Okay, here's a video where you can get more practice on Kaiser problems. I wanted to run through it because MATLAB will actually solve the Kaiser problem in terms of you give some filter specifications and MATLAB will return the filter order, the Kaiser parameter alpha, and let's say the cutoff frequencies that you need for either band pass or low pass or high pass or whatever. Okay, so I wanted to run through that with some examples that you're already familiar with. The first one is an example out of the book. Okay, so from the book you're supposed to do this low pass design using the Kaiser window method. Low pass operating frequency is 20 kilohertz. Pass band starts at 4K, stop band stops at 5K. The pass band has 0.1 dB of ripple and the stop band has 80 dB of attenuation. Okay, so what you do here is you calculate the from the pass band and from the stop band specs, you calculate the deltas. Okay, so we know how to do that, and then you give the MATLAB command the frequency cutoffs. Okay, and so in this particular case, we know that it's low pass, so it's looking like this: 4,000, and then 5,000 is the cutoff for the stop band. Okay, and so we know that our filter has to achieve this kind of template where it's the frequency response lies in this range. And so what MATLAB expects is you to give this a range of deltas. Okay, so we have a delta that's associated with the pass band, and we have a delta that's associated with the stop band. And we calculate those just using the formulas that we did for Kaiser. All right, so you give it the cutoffs, and then the thing that's different here is you tell it what the magnitude response is supposed to look like in the ideal case. Okay, so we're given two numbers here, 4,000, 5,000. That comes from the frequency cuts. All right, we know we want this to be ideally 1 in the pass band, and then from the stop band, we want that to be ideally 0. Okay, so that's why you give it this vector, 1 and then 0. That's a low pass filter. All right, then you just plug in with the arguments that you've come up with, and it will return the order of the filter, the cutoff frequency for the desired response, the one that you need to window with the Kaiser window. But that's given in FN, okay, so that's normalized frequency in MATLAB, and so you can convert that. Remember, normalized frequency in MATLAB is normalized to the Nyquist rate, so if you unnormalize it, so take FN, multiply it by Fs over 2, and then convert that to samples per second, which means divide by Fs and then multiply by 2 pi, you will get the cutoff frequency in radians per sample. Okay, so you go through this template every time and you can get the answers. All right, it will tell you what the order of the filter is. Okay, it will tell you alpha, it will tell you omega n. All right, the catch is, if you look at this in the book, this is really close to the right answer, but the catch is, in the book they said inexact is 101.3 or something like that. I don't remember the exact number, but from there we rounded up to 103. MATLAB, they make it clear in the documentation that this is just getting you in the ballpark and you have to test it. Okay, so they return 101, which is really close. And so if you did this by hand and you got inexact to be 101.3, you'd feel pretty good about that answer. Okay, so I ran this on a problem that comes from the book. All right, so that you could do that yourself if you wanted to come up with different Kaiser window problems to practice with. Okay, so let's do another one. This second one comes from the problem that I assigned to you as practice, and there's already a video solution for this. Okay, so let's run through the MATLAB commands that produce the same solution. Okay, so the MATLAB commands in that case look like the following. Okay, we were given a pass band spec of 1.5 dB, the stop band attenuation of 60, Okay, so we plug those values in. Okay, pass band, stop band, calculate delta pass, calculate delta stop. The cutoff frequencies are 4,000 and 5,000. Okay. All right. Actually, that's wrong. Okay, so sorry, I got it right here. In the problem that I gave you, the cutoff was 4,500 hertz, so make that change. Okay, and so with that, we put in the cutoffs. We want this to be a low pass filter, so it's the magnitude is 1 up to 4,000, and then from 4,500 on, ideally it would be 0. Okay, so that's the 1 and then 0. That's what this term is. We've got the deltas calculated. We calculate the order alpha and omega n. So these match exactly with the solution that I gave you in the previous practice problem. Okay, so now that we've done that, that gives you an idea of how to use the Kaiser order MATLAB function, and so you can practice all you want. You just make up your own filter specifications. Okay, so I did one here. Okay, just to illustrate this, let's determine the order, the shape parameter alpha, and the cutoff omega c for an FII Kaiser bandpass filter. Okay, so for bandpass, we have 4 frequencies of interest, right? We have the passband frequencies in the middle, and then there's stop band frequencies on each edge. Okay, so I can quickly draw a picture of that, and I think you understand how that would work. Okay, we know that at 2,500, we want ideally the response to be 1. At 5,000 is when that stops. And then coming here at 6,000, we want that to be 0 from here on out. Okay, and between 2,000, so 2,000's right here, we want that to be 0. So the mag command is 0 from this first 0, 1, and then 0, 0, 1, 0. Okay, so we actually have 2 stop bands in this case, the stop band on the left hand side and the stop band on the right hand side. So when I specify the deltas, I give it a delta stop, a delta pass, and a delta stop. Okay, so when you're running through this by hand, which delta do you use? Well, you calculate the delta stop on both sides. In this case, they're the same number because the specifications were the same on both sides, but it wouldn't have to be that case. All right, so you choose the smallest of these that will work. Okay, choose the smallest and then apply the Kaiser method. All right, so from there, you're ready to go. You can plug in the cutoff vector, the magnitudes, the deltas, and fs, unnormalize, and then normalize again to get radians per sample, and you get these answers. Okay, n equals 64. You've got 2 frequencies, right? Omega B and omega A. Okay, that's B, and this is B. This would be A. The D of K is the bandpass formula. Okay, and we know what alpha should be to make these specifications. And so, you know, here's an example of how you can apply the Kaiser MATLAB function to get practice problems. All right, so I do want to notice that's an even number. Okay, so MATLAB has a way of implementing an even numbered order Kaiser filter. Okay, what we've done in our class is we've moved up to n equals 65. All right, so it never hurts to move up by 1 or 2 values of n, and that'll just improve things in terms of meeting the minimum specs for your filter. All right, so there you have it. A way of using MATLAB to check a lot of answers that you might want to practice with the Kaiser method.